There's this incredible invisible force that's shaping our world, all the way from the planet's core right up to the tech you're holding in your hand. Ever wonder what paints the sky with the northern lights? Well, you're looking at it. Today, we're diving deep into the concept of the magnetic field.
Okay, so here's our game plan. We're going to start with a totally accidental discovery that basically rewrote the physics books. Then we'll figure out what a magnetic field actually is and how we can see these invisible patterns. After that, we'll see how electricity is the magic ingredient. And finally, we'll put it all to the test with some real-world puzzles. Sound good? Let's get into it.
All right, so our journey doesn't start with some crazy complex equation. Nope, it starts with a story. And it's one of those classic moments in science, A simple, totally unexpected observation that happened during a lecture and ended up changing everything we thought we knew about two of the most basic forces in nature.
So before we dive into that story, let me ask you this. What on earth could a plain old copper wire and a simple compass possibly have in common? I mean, they seem totally unrelated, right? Well, it turns out their bizarre interaction is the whole reason we even have a field called electromagnetism today. Okay, so the main character in our story is a guy named Hans Christian Ørsted. Let's set the scene. It's 1820. He's up in front of his students, giving a lecture, and he's just doing a routine demonstration with a simple circuit, a wire and a battery.
And just sitting there on his lecture table, completely by accident, was a magnetic compass. The second he closes the circuit and that electric current starts flowing through the wire, the compass needle jumps. Now think about that. A compass needle should only move if there's a magnet nearby, but there were absolutely no magnets anywhere near his setup. So what just happened?
The conclusion he came to was just inescapable. And honestly, it was huge. The electric current moving through that wire had to be creating its own magnetic field, a field that was strong enough to physically move the compass needle. This was the moment. For the very first time, someone had proven a direct link between electricity and magnetism.
Okay, so Ørsted proves that an electric current creates a magnetic field. Awesome. But that just leads to the next big question, right? What is a magnetic field, really? How do you even begin to define this invisible force? Well, in a nutshell, it's just a region of space. But it's a special region where if you put a magnetic material, it's going to feel a force, a push or a pull. And here's the cool part. That force has both a strength and a direction at every single point in that space. That's why scientists call it a vector field.
So, how do we see this invisible force? We use this brilliant idea called field lines. And these lines have to follow three simple, totally unbreakable rules. Rule 1, they always flow out of a North Pole and into a South Pole. Rule 2, they are smooth curves that can never, ever cross each other. And Rule 3, the more crowded the lines are, the stronger the magnetic field is in that spot. Simple, right? And you can actually see this for yourself. It's such a cool experiment. If you sprinkle some tiny iron filings around a magnet, they don't just land in a random pile. No way. They physically snap into formation, perfectly aligning themselves along these invisible field lines. It's like they're tracing the blueprint of the force right before your eyes.
Okay, so let's keep those three rules in our back pocket. North to south, no crossing, and density is strength. With those in mind, let's check out some of the classic patterns these magnetic fields actually form. First up, the absolute classic, the single bar magnet. And you can see it right here. The field lines pour out of the North Pole, they loop around through space in these beautiful, smooth curves, and then they dive right back into the South Pole. They form these perfect, continuous loops.
But now check this out. Look what happens when you bring a North Pole and a South Pole close to each other. Those field lines just reach across the gap, connecting directly from north to south. You're literally looking at a picture of attraction. This is the force that's pulling them together.
Okay, but what if the fields are working against each other? Imagine a magnetic tug of war. If you have two forces pulling in opposite directions, and they're perfectly equal in strength, what happens? Well, they cancel each other out completely. That specific spot where the net force is zero, we call that a neutral point. And you can see a perfect example of that right here. We've got two like poles, two north poles, facing off. See how their field lines are pushing away from each other? That's repulsion in action. And right there in the middle, where that X is, that's our neutral point. The push from the magnet on the left is perfectly canceled out by the push from the magnet on the right. No force, right there in that spot.
All right, let's circle back to where we started, with Ørsted and his wire. We know the current in the wire made a magnetic field, but what shape was it? What direction was it pointing? How do we figure that out?
Well, there's this fantastic and super simple trick for this. It's called the right-hand grip rule. Seriously, you can do this right now. Imagine you grab that wire with your right hand. Now, point your thumb in the same direction the current is flowing. The way your fingers naturally curl around that wire, that's the direction of the magnetic field. It's a series of perfect circles wrapping around the wire. Okay, so a straight wire makes circular fields. What if we get clever and coil that wire up? Loop after loop after loop. Well, that's called a solenoid. And here's where it gets really amazing. When you run a current through that coil, the little circular fields from every single loop all add up. They combine to create one big magnetic field that looks, you guessed it, almost exactly like a standard bar magnet. And just like that, you've built an electromagnet.
All right, theory's done. We've got the rules, we've got the concepts. Now let's put it all into practice. Let's solve some magnetic puzzles and see if we can figure out what the field looks like in a few different situations.
Okay, first example. Get this. You've got a magnet shaped kind of like a donut. The North Pole is just the small circle right in the middle, and the South Pole is the entire outer ring. So, what do the magnetic field lines look like in the empty space, in that air gap? Let's just apply our rules. We know the lines have to go from north to south. So, they have to come out of that center North Pole and travel across the gap to the outer South Pole. They're going to shoot straight out from the center in every direction. What you get is this amazing starburst pattern, pointing radially outward. Okay, practice question number 1. Super simple setup. You bring the south poles of 2 bar magnets close together. Draw the magnetic field. What's it gonna look like? Okay, let's think. Like poles repel, right? And the field lines for a south pole are all trying to go in. But we have a rule. They can't cross each other. So what happens? They're going to be forced to bend away from each other, pushing outwards. This leaves a big empty space, a weak zone, right in the middle. That's where you'd find a neutral point, where the two fields just cancel each other out. All right, last practice question, and this one's a little trickier. Picture 2 bar magnets lying parallel to each other, but they're pointing in opposite directions. So the top one is south-north, and the one right below it is also south-north. The puzzle is sketch the field and tell me where you'd find the neutral points.
Okay, let's break this down. For each magnet, the field lines loop from its own north pole to its own south pole. That's standard. But look at the space between the 2 magnets. The field from the top magnet is pointing in one direction, while the field from the bottom magnet is pointing in the complete opposite direction. They're fighting each other. So, somewhere in that middle zone, there has to be a point where their strengths are equal and opposite, a point where they cancel out. And that, right there, is where you'll find your neutral points.
Whew, okay, we have covered a ton of ground. We went from Ørsted's lucky accident all the way to mapping out these complex patterns. So let's do a super quick review of the most important things to remember, and then I've got one last thought to leave you with. So, if you remember nothing else, remember these 3 things. 1. A magnetic field is a region of force. 2. Its direction is always, always from north to south. And 3. The ultimate source of all magnetism is moving electric charges. That's the whole ballgame. And I'll leave you with this to think about. We need all these tools, compasses, iron filings, just to get a glimpse of these fields. But get this, animals like pigeons and sea turtles can actually feel the Earth's magnetic field. They use it like an internal GPS to navigate across the entire planet. So it really makes you wonder, right? What other invisible forces, what other fundamental parts of reality are all around us, but we just don't have the senses to perceive them? What else are we missing?